Okay, good morning, everybody. Thanks a lot. Thanks, Roberto, Giuseppe, and Emanuela for putting together this school, which has been great so far, and I hope I will not destroy everything. So I will tell you a little bit about light scattering. How can we do and what can we learn by doing light scattering experiments or other kind of scattering? That's why this is in parentheses on materials to which we apply some kind of stress or strain. And I like to show these data that come from the work of a group of Van der Gucht as a motivation to why we should be interested to do some kind of experiments that tell us something about the microscopic structure and dynamics of a system while we're doing some kind of rheology experiment. So these data were taken on a polymer network in a creep test. The creep test is as follows. You apply at time zero a constant stress and you keep the stress constant, and the sample in general will deform continuously as a response to this step stress. So if you apply a large enough step stress, this is what you would observe. This is the deformation as a function of time. The sample essentially immediately starts deforming and keeps deforming continuously. And mind that this is a logarithmic scale, so it really deforms, it flows, it deforms a lot. But there is something very interesting that occurs if you apply a stress which is a bit smaller, and you have this delayed failure behavior, where upon applying this step stress, basically nothing happens in terms of deformation of the sample. It stays there for extended periods of time. It depends a bit on how big is the stress that you apply, but it can stay there for thousands of seconds. And then suddenly the strain goes up here almost vertically. It means that your sample is failing, is breaking apart, and immediately it flows. Clearly, there must be something that goes on at the microscopic level here that eventually leads to this macroscopic failure. But if we just stick to macroscopic quantities that we measure by rheology, it's very difficult to understand what exactly is going on here. So there are many systems that behave this way. There are other situations where we really need to understand what is going on at the microscopic level, and this is why we would like to do this kind of experiments. So, in principle, what you can do is to put your sample under a microscope. Ooh. Okay, this is a movie by Roberto's group. I think this is emulsions with tracer particles embedded in it. So you apply a deformation and you watch what's going on, and you can track these tracer particles and learn something about the way they rearrange and change position over time while you're applying, for example, this oscillatory strain, but it could be also a creep experiment or some other kind of rheology test. So now I will focus on dynamics. And so I think that there are two natural questions. Why should I focus on dynamics rather than structure? And why should I do light scattering, which is a less direct method as compared to microscopy? I can take these very beautiful movies and look at how the particles move around. Why on earth should I do this complicated light scattering experiment? So these are my answers, I hope. Yes. Okay. Why dynamics? Well, most of the time I will be dealing with samples that are amorphous solids, like gels that are disordered or concentrated suspensions of particles that are not in a crystalline state. And for these amorphous solids, it's not so obvious to pick up any kind of change in the structure. For example, in a crystalline sample, when you apply a deformation, you can follow how defects in the crystal migrate under these forces that you're applying. And this is something that is pretty obvious to do just by watching at your sample. But in a colloidal glass, for example, which is a disorder, which has a disorder structure, it's not really clear what should I look in terms of structure to pick up something interesting. The other point is that these systems like gels and glasses typically have dynamics that are extremely sensitive to small changes in the control parameters, which is not the case for the structure. For example, if you change, for a sample just at rest, if you change the volume fraction or the interaction potential or the age of the sample, that can lead to enormous variations, orders of magnitude variations in terms of dynamics, whereas the structure remains essentially unaffected. So dynamics are much more sensitive than structure for these amorphous materials. Why light scattering or other kind of scattering? One interesting feature is that these methods are sensitive to motion on very small length scales. You can go down to nanometer length scale or even sub-nanometer length scale in terms of the smallest change of position that you are able to measure with light or X-ray scattering. This is not the case for microscopy. The other very important point is that in microscopy, if you want to pick up teeny tiny variations of the particle position, for example, you have to zoom in to use a high magnification objective, but then the field of view is restricted. You are only looking at just a small portion of your sample. So in all imaging techniques, typically, there is a direct proportionality relationship between the size of the field of view and the smallest size over which you can pick up motion of the particles. And this is not the case in light scattering, where you decouple the sensitivity to motion from the sample size. You can pick up this 1 nanometers motion on a sample which is 1 meter big, if you wish. And the other important point is that light scattering is, or scattering in general, is very versatile in terms of what kind of systems you can look at, because you don't need to be able to actually distinguish particles. You just look at the light scattered by whatever you have in your samples. It could be particles, but it could also be polymers, or it could be surfactant entities that form micelles or some other kind of phases. A whole zoology of samples that most of the time you cannot see directly if you do microscopy. So this is why scattering can be a useful technique. Okay, so you have here Roberto Cerbino. Roberto Cerbino is one of the two inventors of this dynamic differential dynamic microscopy method, which combines microscopy and scattering. So I will not have time to go into that, but you should grab him and ask tons of questions, and he will be more than happy to discuss about differential dynamic microscopy with you, which is certainly a very powerful method. Okay, so now that I hope I've convinced you that this is worth going through, this is my outline. Who is familiar here with light scattering? Wow. Who knows what a speckle is? Aha. Okay, so it's not the same subset of people. Interesting. So I think that I still need to tell you a little bit about dynamic light scattering and other techniques that are sort of the offspring of dynamic light scattering. And then I will switch to dynamic light scattering under strain. So Simon has pointed out that strain is the most important thing in rheology, and it's certainly the most important thing when you do a light scattering experiment, because you are sensitive to motion and not to stresses. And in particular, we'll discuss the dynamics due to a change of the strain field in your sample. And then I will introduce a funny technique, light scattering technique, which we term photon correlation imaging, which is a sort of blend between imaging and light scattering, and discuss the differences between the usual far field scattering and these methods when you are dealing with these changes of the strain field. I will discuss various possible rheological protocols, oscillatory experiments, step strain, step stress, etc., in view of what and how easy and what you can get by doing light scattering experiments simultaneously to this rheological test. One thing that comes about all the time when you do these kind of experiments is the fact that you are dealing most of the time with dynamics that are not stationary. And so you have to use special tricks in order to understand what's going on, because if you do a usual time average, you are mixing different states of your sample, and that's not good. And perhaps I will tell you a little bit about the different kind of setups that you can use to do these experiments. I think that this stuff here is sort of overly ambitious and it will take forever. So don't worry, I will stop at the due time. And if there is something that I cannot cover today, I think I will cover it at the beginning of the next lecture that I will have in 2 days from now. Okay, so Nick can take a short nap because this is stuff that I have recently told about at the Bomban Light Scattering School, and Nick was there. But for everybody else, this is how a dynamic light scattering or DLS experiment looks like. You send some coherent radiation, for example, your laser pointer or laser beam, on a sample that contains scatterers, and you observe with a detector the intensity pattern generated by this by the light scattered by your sample. An important parameter is the angle at which you observe your pattern with respect to the incoming beam. This is the scattering angle theta. And if you put a screen and you look what's going on, you will see that the intensity distribution is not something smooth, but rather it has this speckled appearance. And this is basically an interference phenomenon. This is the result of the interference between all scattered waves originating from each particle. And because the particles are typically randomly placed in your sample, you will have here a random diffraction pattern, as opposed to like a regular set of spots, bright spots that you would observe if you replace your sample here with a diffraction grating. And it's basically by looking how these speckles evolve in time that you learn everything about the dynamics of your sample. Okay, just one warning. When you do this dynamic light scattering experiment, you have to be, in order to interpret your data, under single scattering conditions. It means that the likelihood that a photon is scattered more than once before reaching your detector is extremely low, and you can assume that all photons that reach your detector have been scattered just once. So in practice, if your sample looks like that, you're happy. If it looks like that, maybe you have to worry a little bit. And if it looks like that, okay, you will look like that. But there are tricks in order to learn things for samples that look like that, and I will mention them later on. This is how a typical light scattering setup looks like. You have your laser, you have the sample, and then you have some collection optics. This is not very important. It's just to feed the scattered light at some well-defined scattering angle to a detector, which can be a single point light detector like a phototube or avalanche photodiode, or it could be a 2D detector like a CMOS camera, the same kind of camera that you have in your cell phone. And I will show you that that has some interesting features. And then what comes out from your detector has to be processed in order to calculate an object, which is called the intensity autocorrelation function. We will see in a second what this intensity correlation function is. It is the function that tells you in a quantitative way what the dynamics are in your sample. Okay, so what is the idea behind um, this light scattering method? Here I have sketched just 3 particles. Of course, your sample contains billions of particles illuminated by the laser. This is the laser wavelength, the laser light that arrives. Each particle scatters part of this light in all directions, but here I am focusing only in this particular direction at a scattering angle theta that goes to a particular spot on my detector. And as I mentioned before, if you put, this is a real image, a real speckle image that you can observe if you put a CMOS camera somewhere there, and you have all these bright and dark spots. Okay, so far so good. Now, what happens if the particles that scatter light are not fixed in space, but they jiggle around, for example, because of Brownian motion, or because you are applying a strain to your sample, or for any other reasons? Well, as I've sketched it here, let's imagine that initially you have, now for the sake of simplicity, just 2 particles, and their position, the relative position, is such that by chance the light that they scatter in the direction of the detector is perfectly in phase. Okay, when it reaches the detector, you have here a relatively high value of the electric field, and here's the same. So in this case, the contributions of the light scattered by these 2 particles will add up in a coherent way, and you will have a very bright spot. After some time tau, the particles, each particle will have moved around a little bit, for example, because of this Brownian motion, such that the relative distance between them has changed, and the relative phase of the waves scattered by the particles has also changed. And then, by chance, you can end up with a destructive interference. These electric fields, for example, cancel out. So it means that as particles move around, if you look at your speckles, a bright speckle will eventually become dark, and a dark speckle will eventually become bright. And the intensity of these speckles fluctuate with time, which is exactly what you see if you take a movie rather than a single image of your speckle pattern. Now, the idea of dynamic light scattering is simple. It's simply the fact that if the particles jiggle around very quickly, then the speckle pattern will evolve very rapidly. And if the particles move very slowly, the speckle pattern will evolve very slowly. That's it, basically. And then you have to go through the math to do things quantitatively, but the general idea is exactly what I have just told you. It's quite simple. Hello? Okay? Still awake? Yes? Okay, this is what I was mentioning. If you focus on one single speckle on your detector, what you will observe are fluctuations of the scatter intensity with time. And these fluctuations are sort of chaotic and random because everything here is random, is the interference pattern generated by many particles that are all around in random positions in your sample. But still, you can pick up just with your eye that there will be a characteristic time scale for these fluctuations. It is about what is shown here. On timescales much smaller than that, the intensity hardly changes. And on timescales larger than that, the intensity will have undergone several fluctuations between high level and 0 level or very low level. And this this characteristic time scale is directly related to the time it takes the particles to move over a well-defined distance, which we'll see in a second, is dictated by the scattering angle and the wavelength of radiation that you are using. So basically, you fix the scattering angle and you fix the fact that you're using a green laser rather than an X-ray beam or a red laser, and you know exactly that if this characteristic time is 1 second, that's the time it takes for a particle to move over, let's say, 50 or 100 nanometers. And you know that precisely. So how you know that and what exactly that means? This magic length scale is 1 over q, and 1 over q is what is called the scattering vector. It is directly related to the scattering angle. So let's say that you have here your incoming beam. This is the scattered light. You place your detector at a scattering angle theta. You are working with a source that has a wavelength lambda naught. And then you can calculate this q vector in this way. The magnitude of the q vector is 4 pi. N is the refractive index of a solvent, for example, water, N would be 1.33, divided by lambda naught, and then you have this sinus of half of the scattering angle. The scattering vector is called a scattering vector because it is actually a vector. Yes? No. This is called quasi-elastic scattering. If it was elastic, strictly, it would mean that particles would be completely frozen. It is called also historically quasi-elastic because it's almost elastic, but you have like 1 part in a million variation of the wave vector. And that time-dependent variation is exactly what gives you these fluctuations. You can of intensity. You can analyze things in this way.
Because here you look in Q, mostly you focus on the Q space because you cannot resolve the change of the wavelength. In fact, it's too small. Or could you?
Oh,
could you look at the change of energy?
Yes, I can. Actually, historically, people started doing that, meaning that they used interferometers and spectrometers to measure in the omega, in the frequency domain, the shift of radiation due to the scattering process. But then with the advent of fast electronics, it turned out to be much more convenient to work in the time domain rather than the frequency domain. And that's why people now have forgotten that it's quasi-elastic light scattering. Nobody uses this terminology anymore. But yes, historically, they started looking in terms of energy, so in omega space. Neutron scattering, people do that, yes. Okay, so the q vector is a vector. And why do I insist on that? Because you will see in the following that in many situations where you're doing some kind of rheology experiment coupled to scattering, you have really to think about how your q vector is oriented with respect to the direction of the shear, for example, that you are imposing to your system. So how do I get the q vector and not just the magnitude? Well, I have to consider the wave vector of the incoming beam. This direction. This is the wave vector of the incoming beam, and the wave vector of the scattered beam, which is collected by my detector. This would be the direction, so this is shown here. And the scattering vector is just the difference between the incident, the scattered wave vector and the incident wave vector. So it will be this guy here. In this particular experiment with this geometry, the q vector will be oriented this way. It doesn't matter if it is this way or minus q that way, but it really matters if it is oriented like that or like that, if you are introducing some sort of a symmetry breaking thing in your experiment. So if you're just looking at Brownian motion, there is no symmetry breaking. Brownian motion occurs in any direction with same likelihood. So you don't care about the direction of the q vector. You only care about the magnitude. But if you're doing shearing, for example, in this direction, then it matters a lot if your q vector is oriented like that or like that. And we'll see in the following why exactly. So we have learned what the q vector is. we know that the characteristic time scale of these intensity fluctuations tells us the time it takes the scatterers to move over a distance 1 over q, roughly. Next problem is, okay, it's very nice to say, haha, the characteristic time scale is like that, but I need a more quantitative way to extract this time scale and say it is 1.2 seconds or something like that. And the way you do that is to calculate what is called the intensity autocorrelation function. And this is the thing that people doing light scattering spend all the time looking at and calculating. What is the idea? Well, you take your time-varying intensity signal measured by, for example, your avalanche photodiode or one single pixel of your CMOS detector, and then you ask the question, let's say that I shift in time my original signal, so the blue is the original signal, and the red is just a replica of the blue signal, but shifted by a teeny tiny amount tau. Now I ask the following question. How similar are at each time step the red and the blue curves? Is, for example, here the value of the red and blue curve intensity the same or very close? Yes. If I go here, well, not exactly the same, but quite similar, etc., etc. Clearly, if I have shifted by a very small amount tau, the red and the blue curve will be very similar. They will be, in mathematical terms, highly correlated. So this intensity correlation function quantifies how similar, time by time, are the original signal and the time-shifted signal. If, by contrast, you shift the red curve by a delay tau, which is much longer than the characteristic time scale of these fluctuations, then time by time, on average, there will be no correlation between the value of the red curve and the blue curve. The red curve might be very high, while the blue curve at the same time is very low, and vice versa. So clearly, as you change tau and you increase this time delay, you start from a situation where the two curves are very similar, very correlated. The intensity correlation function is very high. And then this intensity correlation function decays and goes to lower values. And at some point, if you shift a lot, it doesn't really matter if you shift a lot or twice a lot or 10 times a lot, because you end up with uncorrelated signals. So what is, in practice, this intensity correlation function? Is this what is written here? You calculate it by taking the value of intensity measured at some q vector and some time t. You multiply it by the intensity measured at the same q vector and at a delayed time t plus tau. And you can do this calculation for different taus. And then you have to take an average of this quantity. And typically, the kind of average that you take is the simplest average that you can take in an experiment, is just time average. So you calculate your intensity correlation function this way. You do this product time by time, and you integrate over the duration of your experiment, and you normalize with respect to the duration of your experiment. And of course, if you want to get something meaningful, you have to average your experiment over a time, capital T, which is much longer than the typical time of these fluctuations. Otherwise, you don't sample in a proper way all the possible fluctuations that you may observe. So you calculate this thing here for one single tau, and then you repeat it for different choices of tau, and you end up with this intensity correlation function. For tau equals 0, if you plug in tau equals 0 here, this is just the average value of a squared intensity. And for tau, that tends to infinity. In practice, tau much longer than the characteristic time of these fluctuations of intensity. You will have that the intensity at time t and time t plus tau are fully decorrelated, statistically independent, which means that this average here breaks in the average of the intensity at time t times the intensity at time t plus tau. If your system is not changing structure, this average intensity will be the same, so you end up with the average intensity scattered by your system squared. And if you look at this curve, now you have something which is really quantitative. You can fix a criterion. Let's say, okay, I look at the time varying portion of this curve. I define my characteristic time scale of the relaxation of motion of the particles over a length scale 1/q as the time it takes to decay by half of this time varying part, for example, or 1/e. You decide the criterion, but once you have decided the criterion, you can compare different systems, you can do things quantitative. And actually, you can calculate what is the shape of this function here in various situations that are of interest. Let me go back a second on this business about the time average. What we can do experimentally so far is just a time average, okay? So we run our experiment and we get this thing here. What we are really interested, it's rather what is called an ensemble average. An ensemble average is what I would get if I would repeat this experiment with different cells filled with the same kind of samples, but independent samples. I prepare 1,000 samples. I put 1,000 gels, one after the other one, in my machine. I measure for each of them this product here, and then I average that stuff over all the 1,000 experiments that I have done. This is unpractical. So for the time being, we will stick to time averages. I will tell you a little bit later that there is a trick to get something which is closer to these ensemble averages. But we have to keep in mind that there is a difference in principle between this time average that we measure and this ensemble average that we wish to get. And typically we can calculate, for example, or get from a simulation if we do multiple realizations of our systems. That's the kind of thing that we get. So if we want to compare our experiments to theory or simulations, we need to keep in mind this difference between time average and ensemble average. Okay, just to give you a feeling of the timescales that are involved, this I told you this duration of the time average of your experiment has to be much longer than the characteristic time that you measure here. What is much longer? Well, if you are super sloppy, it's like 100 times longer, but this is really bad. You will get super noisy data. If you are so-so, you will do 1,000 times. If you want really good data, you will do 10,000 times, okay? So now the key point is, what is this relaxation time typically? If you take Brownian motions, let's say Brownian motion of particles at about 100 nanometers, measure the scattering angle of 90 degrees in water, blah, blah, blah. This is something like 1 millisecond. So 1 millisecond times 10,000, that's 10 seconds, no big deal. But if you go to gels, glasses, concentrated suspension, and blah, 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 this relaxation time can be 1 day. And so then 1,000 days, it's too much. So we really have an issue about this time average when we are dealing with systems that are gel-like, glassy-like, and so forth. But I will show you that there are tricks to address that. Normally, people don't like working directly with this correlation function because it is not a normalized quantity. So you will just normalize this way and you subtract 1. This is because if you do things this way, your intensity correlation function goes from something that is setup dependent, is not very important, it's close to 1, it decays all the way to 0. So this G2 minus 1 stuff is the thing that everybody doing light scatter will tell you about. My G2 minus 1, my G2 minus 1 is that, blah, blah, blah. All the time we'll see this G2 minus 1. It is just this time, normalized time autocorrelation function, and the decay, the characteristic decay time, once again, is the time it takes particles to move over a distance of order 1 over q. Now, it turns out that this intensity correlation function is directly related to what is called G1, which is the electric field correlation function. And this is known as the Siegert relation. G2 minus 1 is just, besides a setup dependent prefactor, is G1 squared. Okay, but why should I care about G1 squared? The reason why I should care about G1 squared is that G1 squared is something that now has a direct relationship with theory and simulations. It's what is called the intermediate scattering function, ISF. And here is its expression for a set of particles. It is an exponential of IQ vector dot product with the position of particle j at time 0 minus the position of particle k at time tau. And then you do this double sum, and you normalize with respect to the same quantity but calculated for tau equals 0. So this intermediate scattering function is important because if you go to your simulation body and say, hey, Giuseppe, what is the ISF for this and that system? And Giuseppe knows the answer and tells me. If I go to him and say, I have this G2 minus 1, I say, well, what? I don't want G2 minus 1. I want the intermediate scattering function, okay? But you can get it from your experiment. Okay, this is the coherence factor. It's called that's not important. This is not important, and this we mention it. Okay, now dynamic light scattering has various offsprings. Everything in this field started with dynamic light scattering in the single scattering limit, but then people have worked out various, let's say, variants of the technique that you can apply in different experimental situations. So let me just mention a few of them. The first thing I would like to mention is multispeckle methods. So multispeckle methods were introduced in the late 90s. And the idea is the following. Imagine that now we do our light scattering experiment with a 2D detector, like the CMOS camera of your phone. This is what a typical speckle pattern would look like. And for the sake of example, this speckle pattern has been measured in a low angle scattering experiment. Basically, you shine your laser beam onto your sample and you place your detector very far from the sample, such that a small distance on the detector corresponds to a teeny tiny scattering angle, okay? What you can sort of see here, this is a beam stop that will basically block the transmitted beam, the light which is not scattered by the sample. This is because typically this unscattered light is much brighter than the light scattered by the sample because we are in the single scattering limit. So most of the light just goes straight through your sample. For example, if you take this, bottle, and you shine your laser beam there, most of the light will just go through your bottle, and just a teeny tiny fraction will be scattered. And if you put a screen over there, you will observe something like that. Now, the idea of the multispeckle method is to say, okay, for example, let's take this box here on my detector. Each pixel here corresponds to a slightly different Q vector because the Q vector here changes as you move out from the position of a transmitted beam. But still, if I'm not too picky, I realize that, okay, it's not exactly the same Q vector in this box, but it's roughly the same Q vector. So maybe something that I can do is to calculate an intensity correlation function for all the pixels in this box here. And rather than doing a very lengthy time average, I replace this time average by an average over what I calculate for each pixel within my box. Okay? I can choose this box here. I can, if I have a fully isotropic system, what really matters is not the orientation of a scattering vector, but just its magnitude. And in this geometry, the same scattering angle, but oriented in different ways, corresponds to a ring of pixels centered around the position of the transmitted beam on my detector. So I can calculate my intensity correlation function for each pixel of this ring, and then just average over all pixels of the ring. I like to deal with normalized quantities, so I will just normalize this thing here, which has been named as CI, the correlation of intensity. I can normalize it the same way basically I would do for my G2 minus 1. Once again, here averages are averages over pixels belonging to the same ring or the same box. And then I subtract 1. So what is the relationship with the usual intensity correlation function G2 minus 1? I have basically averaged a little bit over Q vector, but paying attention to restrict my average to a set of Q vectors that are really very close. So I've not messed up things because I'm not mixing things measured on different length scales. Keep in mind that if I change the Q vector, I change the length scale, okay? So this is a sort of intensity correlation function average over this small range of Q vectors. If I further average it over time, then I go back essentially to the usual G2 minus 1 function. So why should I do this thing here, which is more complicated? I have to use a 2D detector, blah, blah, blah. Well, what I gain is the fact that basically if I average here over 10,000 pixels, it is the same thing as if I had averaged this thing here over 10,000 times the relaxation time. So I can make my experiment much, much shorter. I can measure things like the gels, the glasses, et cetera, that have a relaxation time of 1 day, because essentially I just need to run my measurement for 1 day. Even more importantly, I can static dynamics that are non-ergodic. I don't want to go into the details, but one can show that this pixel average, to some extent, is equivalent to do an ensemble average. And then the final thing is I can address dynamics that evolve with time. Since I don't have to do a very long time average, if my dynamics are evolving with time, okay, I can do a short measurement here, and then another short measurement a bit later, another short measurement a bit later, and I will get the full evolution of the dynamics. So this is quite convenient. XPCS. XPCS is, yes?
So you're saying that the measurement results for different theta angles are essentially independent in this experiment.
So if you move from one speckle to another one can show that each speckle is associated to a specific Fourier mode of distribution of particles in your sample, and distinct Fourier modes are full independent. So the fluctuations of one speckle are completely decorrelated from the fluctuations of a neighboring speckle, which means that distinct speckles bring statistically independent information. That's why it works. Yeah.
Another question. P is it means a pixel.
P means a pixel.
But the double average, I don't get. You average, you take the intensity of one pixel, and then you average over the intensity of the circle.
Where? Here, for example?
On every average.
So that means do the sum for all pixel P belonging to the box or the circle and divide by the number of pixels.
Yes. You average for a given norm of Q. I mean, you do an average over angle or
Again, it depends. It depends. If the sample is isotropic, the orientation of Q doesn't matter, so I can take the ring. If I'm doing shearing in this direction, for example, then no, I cannot do this ring average. I have to pay attention to the orientation of Q.
how can you combine the data from different Q vectors?
I mean, if the sample is not isotropic, I cannot.
You cannot, okay.
I have to use the trick of a small box, saying, okay, the box is small enough such that whatever happens within the Q vectors associated to that box, that's the same. And I'm just averaging. But I cannot take the ring because things may be different in this direction or that direction.
Because of course you point out the issue that you have this problem of time of getting the ergodic average. In principle, we should think that we can get ergodic data also using the spatial average. But the problem here is that in order to get a speckle, you need to shine a very small area. So in fact, there is an issue also of the size of the system that you're probing, right?
Okay, this is a super nice question, a little bit technical, but I try to escape from this question saying that you get something which is more or less the ensemble average. The answer is, this is true as long as you illuminate a portion of your sample that contains several regions statistically independent and each representative of the full system. In practice, that's almost always the case. That's always the case, I would say, for the structure. That's not necessarily the case for the dynamics. And this is a great matter of discussion later on. Okay? But in practice, your beam will be at least 1 millimeter in section or more. And that corresponds to, if you take a correlation length of, let's say, 100 microns, which is the biggest that you can imagine in this kind of systems, that's still a lot. That's not necessarily a lot for XPCS. XPCS is this thing here. You replace this 20 euros laser pointer by a 20 billion synchrotron light generator, and you do the same thing with X-rays, okay? But it's conceptually absolutely the same thing. So you need to go to these fancy places to make a proposal to get beamline and so forth. The difference is that you can access typically smaller length scales because the wavelength of X-ray is much smaller with respect to light. You typically do in the low angle geometry, which means that looking at different rings, you can get things at different Q vectors, which is interesting. It's nice because sometimes you have samples that are too turbid for dynamic light scattering and are fine for XPCS. You use this multi-speckle approach typically. One thing that you have to keep in mind is that this X-ray beam can actually burn or modify or screw up your sample. So you have to check for that. The other thing, another offspring of regular dynamic light scattering is diffusing wave spectroscopy. And this was designed precisely to address this kind of samples, so very turbid. In these samples, the idea is that you shine your laser beam in this milky stuff, and the light will be scattered a lot of time. So if you follow a photon, it will undergo a sort of random walk within the sample like that. and finally get out and be detected by your detector. So we can think of this experiment, imagining that these photons undergo a random walk, and the step of this random walk is called L star in the literature, is the photon mean free path. It depends on the sample, but it's typically something between 10 to 100 microns or something like that. One thing that is important to keep in mind is that here you are probing motion isotropically because of this random walk propagation of the photons. So the random walk is isotropic. So even if your dynamics are anisotropic, they will be probed averaged in all directions because the photon goes in all directions. The very interesting feature about this experiment is that it is extremely sensitive to small displacements. Why is that? Basically, the idea is that what is important here is the change in phase of the photons that go through the sample. And since they undergo tens, hundreds, thousands of scattering events, even if each particle moves by that teeny tiny bit, you add up all the change in phases during the propagation of the photon due to these teeny tiny changes in particle position, and you get something which is comparable to the wavelength of the light, which is the condition in order to change a speckle from bright to dark. So in practice, it depends if you do your experiment in transmission or in backscattering, but you can go down to less than 1 nanometer if you do your experiment in transmission, meaning that you put your detector on the opposite side of laser. And otherwise, it's more like in the tens of nanometers if you put your detector on the same side of your laser. Okay, let's recap what we have learned about dynamic light scattering. We have learned that it's sensitive to the relative motion between particles, because here, remember that our intensity correlation function is proportional to the intermediate scattering function squared. And here you have this difference in particle position. You don't care if all your sample undergoes a rigid translation. Usually in light scattering, you don't see anything. You will not notice that. You are not sensitive to that because the relative distance here will not change if everything does like that. There are exceptions, we'll see later. In single scattering, we probe a length scale of the order 1/q, so it depends on scattering angle. It can be from tens of nanometers to about 10 microns. For XPCS, this is smaller, it's typically between 20 and 600 nanometers. We have seen multiple scattering, length scale it's much smaller. We have seen multi-speckle methods that drastically reduce time averaging. I didn't mention that explicitly. I've shown you multi-speckle methods applied to dynamic light scattering, but you can apply them exactly the same way to X-photon correlation spectroscopy. That's easy. We just said that it's the same thing except that you replace your wavelength. And also to this diffusing wave spectroscopy thing. Okay? Oof. So we did point 1. And now we try to do point 2. Dynamic light scattering under strain. Okay. Now, if we do dynamic light scattering under strain, we have to think about what are the kind of motion that lead to a decay of the correlation functions that we are measuring. There is thermal motion, Brownian motion, rattling in the cage is the motion that is observed in colloidal glasses, strand vibrations in a gel, all these kind of things that we also have for a sample at rest, okay? So that, in principle, it's not what we care about if we are doing rheology, but we have to keep in mind that they exist and we can measure them separately just on a sample at rest. There may be slow relaxation. This is typical of samples like gels and glasses. In principle, you would think that everything is frozen, no possibility of really change a lot the particle positions, but experimentally, people have found out that that's not the case. There are very slow relaxations. They might be related to thermal motion on very long time scales. They might be related to internal stresses that are frozen in when you prepare your sample, and Mehdi has mentioned that. The time scale here, it's typically hundreds or thousands of seconds, okay? And then 3 and 4 are the things that we are really interested in if we are doing rheology and light scattering or scattering simultaneously. One thing that changes the position of the particles are plastic events. Imagine, for example, if you have a foam and you have these T1 events where a foam switches neighbors, that will locally change a little bit the position of the bubbles in the foam. So at least locally, you will get a contribution to the decay of the correlation function. In a gel, if you have a bond that breaks, well, locally you have a strand that was like that, perhaps, and when the bond breaks, it's like that. So you have moved things where this event has occurred. Then there is something which is more subtle, but it is at least as important, maybe even more. You have to think that in general, when you do some kind of rheology experiment, you have an evolution of a strain field in your sample. And light scattering is also very sensitive to that. What do I mean by evolution of strain field? Well, that might be, imagine that you have a startup shear experiment. So you start shearing your sample like that. You have an evolving strain field in your sample. Even if the sample was a perfectly homogeneous elastic material, particles will be displayed because of this strain that you apply. So that gives you some decay in your light scattering experiment. But even this 0.3 will give some strain field in the sample, because imagine again your gel network. You break something here, okay? But Mehdi has shown us that if you take a gel, then you will have part of the gels at rest that will be under tension, other parts under compression, and so forth. So if you break your network somewhere, the whole network, even far away from this localized event, will rearrange in order to redistribute the stress that has been generated or modified by opening this bond. And so you will have a local change of position where the event occurs, but then you will have a far field deformation in your sample that you will pick up with these scattering methods. So what I would, since this thing here, the evolution of a strain field, is really important, both when you just think of your rheological protocol and in response to a local event, I want to spend a bit of time on it. So the question that we have to ask is, what is the relative motion delta R that we observe in our sample following a change in the strain delta epsilon? Here, delta epsilon, I want to be very general. It's a change in the strain. It could be the global strain if I am applying strain varying deformation to my sample, but it could be also the change in the local strain or mesoscopic strain field across the sample in response to some event. So if we think in terms of dimension analysis, well, we know that relative motion delta R has to be the change in strain delta epsilon times some characteristic length scale. And this L is some relevant length scale, which depends on the kind of experiment. And we have to think a little bit, what is this L for the different kind of experiments that we can do. So let's start from diffusing wave spectroscopy. What is this L? Well, it turns out that this L is actually not related to the sample geometry. This is a bit surprising, but it's related to this characteristic length scale of the random walk of the photons. So this, it turns out that this characteristic L is just L star, the photon mean free path. So if we apply some given strain change delta epsilon, the typical change in particle position detected by DWS will be simply order of magnitude L star times delta epsilon. Example. So this thing here was a piece of plastic material which was illuminated by a laser beam, and we were pulling on this material, so applying an elongation at a fixed strain rate. And we measured that this piece of plastic is whitish, so we are doing an experiment in the diffusing wave spectroscopy limit, the highly multiple scattering limit, and these are the famous G2 minus 1 correlation functions that we have measured. So if I tell you, okay, what was the strain increment over the characteristic decay time of this correlation function? Well, this is about 7 seconds. So I know that delta epsilon has increased over 7 seconds by an amount which is delta epsilon. I mean, the typical relative displacement has been over these 7 seconds, delta epsilon times L star, okay? Now, since I'm doing this experiment, I was doing it in backscattering, one can show that the typical length scale to which you are sensitive in backscattering is of the order of the wavelength of light of my laser divided by 2 pi. So I can figure out what was this delta epsilon over a time of 0.7 seconds. It was lambda divided by 2 p L star. Here lambda was about 500 nanometers, let's say 0.5 microns. And then I had to divide by 6, let's say 2 pi is 6 times L star. Here it's typically 100 microns, something like that. So you get that this corresponds to a strain increment of the order of 10 to the minus 4. Okay? If I got it right, you check. So that shows you that you can work out exactly what the delta epsilon was, and that you are really sensitive to teeny tiny changes of a strain. Measure 10 to the minus 4 in strain increment, it's not so obvious. One can do things more precisely. I don't want to go through the details. I will give you the slides if you're interested. Just the main point is that there is a standard formalism that applies to any kind of sample, not necessarily during a rheological test, that converts the G2 minus 1 function in mean square displacement as a function of time delay tau. Okay, this is something that you find in textbooks and so forth. And if you are applying a deformation to your sample, then this mean square displacement is directly related, that you measure by DWS, to a function of a strain tensor associated to the kind of deformation that you are applying. It's just 3, this is L star squared, and this complicated function is not so complicated at the end. This is the trace squared of the stress tensor, blah, blah, blah. You see here the expression. The point is that for simple geometries, you look up in a textbook what the strain tensor is. This is perfectly known, etc., etc. For my tensile test, for example, this is the strain tensor. This new here is the Poisson ratio, which accounts for the fact that as I'm pulling like that, my sample, it elongates this direction, but it squeezes in the other directions. This epsilon dot is the rate at which I was pulling, and this tau is my time delay. So I can exactly work out, for example, what epsilon dot was in my experiment just by fitting my correlation function using this formalism. And this is for a shear test where you're applying a shear at a rate gamma dot in the x direction. So you can work out things very nicely and relatively simply with DWS. Quiz. No quiz. Quiz, okay. What's the smallest increment in strain that you can measure in DWS? As a reminder, you have this thing here, you plug here L star. L star is typically in this range of values. And if you do the experiment in the most sensitive way, which is in transmission, you are sensitive down to a fraction of a nanometer. So if you work out all these things, it turns out that you can measure 10 to the minus 5 increment in strain. So it's amazingly sensitive, which is gorgeous, but not always gorgeous. Because if you're doing an experiment, for example, this kind of experiment where you pull your material, then a teeny tiny change in the strain state of your sample will be detected by this technique here. It means that if you have a local rupture of something, that will give you a huge variation of a strain, and in some sense you will be blinded by this extreme sensitivity. It's as if your eyes are super sensitive to darkness, and when you go out in the sunshine and you don't see anything because you are flooded with too many photons. And here it's difficult, since you are sensitive to these small strains, you are not really able to distinguish between a change in strain status of 10 to the minus 3 as compared to 10 to the minus 2, because anyways, both changes of strain will kill your correlation function. So you have advantages and disadvantages. But if you are looking for something that is extremely sensitive to strain changes, DWS is a good option. Light scattering in the single scattering limit. Yes?
Kind of systems DWS is suitable.
It's suitable.
Yeah, to use.
I would say things that where the motion is restricted. So plastics, stiff elastomers, stuff like that. Okay, single scattering. Now, there is another point that one has to keep in mind. I have alluded to it a few times, but in the single scattering limit, you are sensitive to the relative motion, this difference between Rj and Rk, blah, 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 projected onto the Q vector. You see here, you have the Q vector, and then you have a dot product. So what really matters is how far you are displacing particles, but projected on the direction of the Q vector. So let's take as an example this setup here. This is a sort of a homemade rheometer embedded in a shear cell. So you can move these glass plates with respect to each other like that. And you apply a shear in the direction of the x-axis like that, okay? And you observe, you shine a laser beam through it, and you observe what's going on your CMOS detector. And now if you think a second about the geometry of this setup here, if you look down here, you will be probing a Q vector which is oriented vertically, that is along the y-axis, that is perpendicular to the direction of the imposed shear. If you look on a spot here, which is horizontally displaced with respect to the transmitted beam position, then you will be looking at scattering at a Q vector which is oriented along the x-axis, that is along the direction of shear. So imagine that now you have a perfectly homogeneous, ideal elastic material. You apply a shear. The displacement within the material will be simply proportional to the distance from the fixed plate, and rigorously directed only along the x direction. So if you do so, you will see, if you do your experiment with this Q vector, you will see a lot of decorrelation because you have displaced things along the direction of this Q vector, and zero decorrelation along this Q vector. So if you are interested not in the affine displacement that you would get in a ideal solid, but in deviations with respect to that affine, you better look which one, Qx or Qy? Qy, exactly, because Qy is not sensitive to motion along the direction of the imposed shear. So this is an example of how important it is to think a little bit about the geometry of your experiment if you're doing single scattering, because the orientation of the Q vector at which you measure things is very important. Okay, what is this characteristic length scale in this kind of experiments? Well, in the experiment that I'm showing here, if you think a little bit, the amount of displacements depends on the distance from the fixed plate. So at the end, what really matters is the thickness of your sample. And so in this experiment, it turns out that L is simply the gap between the two plates. And you can show it here. This has been measured by deforming nearly ideal elastic solid. And you take data measured at different Q vectors, but all along the right QX direction of the imposed shear. And you can superimpose most of them if you rescale the imposed strain by the thickness of the sample, because what really matters is how thick the sample. Data that do not rescale are due to the fact that you are illuminating the sample with a spot that has a finite size, so this also matters. Imagine that you have a sample like that, and you shine on it a teeny tiny laser beam like that. Then if you move the back of a sample by a distance that is larger than the spot size, you are illuminating effectively a different portion of your sample as compared to the beginning, so you lose correlation. That's why you have these deviations here. And with Stefano Aime, who was a fantastic PhD student, we went through all these details, and you will find here in these two papers all the details on what you have to care about and what tricks you can play if you want to do things as properly as possible for this kind of examples. Okay, so far we have considered scattering experiments in the far field geometry. That means basically that you are illuminating your sample with a laser beam. Let's say in low angle would be like that, and then look at the scattering pattern very far from the sample. Another yet equivalent way of looking at the scattering pattern very far from the sample consists in placing a lens to collect the scattered light, and look what happens in the focal plane of the lens. If you go through your geometrical optics class, you will see that this is fully equivalent to put the sensor very, very far, and it's more practical in the lab. So people doing X photon correlation spectroscopy, they don't have effective lenses for X-ray, so they're really forced to put the detector like at 30 meters, 10 meters, 30 meters from the sample, but with light, fortunately, we have lenses, and so we can do the experiment in a more simple way. What I'm showing here is scattering at 90 degrees. So you illuminate your sample with a beam that comes like that, and you pick up with this lens, which is called the Fourier lens, because here effectively you obtain something related to the Fourier transform of the particle distribution here. You collect with this Fourier lens light scatter at 90 degrees. Okay, this is regular scattering. This is what normally you will find in textbooks and so forth. There is a variant, yet another offspring, which is called photon correlation imaging, which is a slightly different way of doing scattering. The idea is that now you use your lens to make an image of the sample, much in the same way you would take an image with a camera or with a microscope or something like that. So now you have this dotted line here, which shows the object plane, which is imaged by the lens in the image plane, and you put your sensor in the image plane, okay? So what's the difference? Well, here, each point of the detector is illuminated by light that comes from every point here in the scattering volume. They all end up here, and distinct points correspond to slightly different scattering angles. Here, point A at a given location is imaged in a location A prime on the sensor. At point B, it's imaged on a different location B prime. So if I look at my speckle image, I can say, aha, I see speckles fluctuating a lot here and much less there. And that's because my sample has more dynamics here and much less there. For example, because it's heterogeneous or because I have a localized rearrangement event here and there. So let me show you how this works. We have this imaging geometry. Typically, you have to make sure that you are not mixing light scattered at different Q vectors because this is always bad, but that's easy to do. An interesting feature is that now if your sample is drifting like that, because you're making an image of a sample, you will see your speckle pattern also drifting like that. So you can pick up this drift motion, you can correct for it, you can measure it, you can do all sorts of interesting things with it. And now our degree of correlation CI, which was this multi-speckle stuff, well, we can do it in a different version where we take boxes in our speckle image, and we know that each different box corresponds to a different location in the sample. So now, if we look at what happens in distinct boxes, we get information on the dynamics in distinct parts of the samples. And this is what's shown here. My degree of correlation now depends also on location R in the sample. What is the relationship with the usual correlation function? The usual correlation function G2 minus 1 averages over time, but also over the whole illuminated sample volume. So if I take this guy here and I further average it over all possible locations in my speckle image and all times, I get the usual G2 minus 1. So let me show you a practical example of why this thing here could be interesting. This is the plate of a rheometer, which is illuminated from the bottom with a laser beam, and we are collecting the scatter light. And we divide our speckle images in boxes. Each big pixel here corresponds to a distinct box over which we calculate this degree of correlation. So if I calculate this degree of correlation at some point during my rheology experiment, which was a creep experiment for an agarose gel, I get basically a high level of correlation, which means essentially no dynamics. Everything is frozen, except a teeny tiny bit of motion up here. And then as the creep experiment proceeds, I see that this dynamically active region expands like that, and eventually it invades the full sample. And when it invades the full sample, that is when the shear rate that I measure with the rheometer goes up by orders of magnitude. That is when, in practice, my agarose gel fails. It does not sustain the stress anymore, and then the sample moves like that. So if I play this movie here, which is just a sequence of these dynamic activity maps, we call them, taken at different times during the evolution of the creep experiment, I can measure this. I can first notice this nucleation in a specific spot of what will be the origin of the failure of this gel, and then the fact that slowly it propagates. This occurs on thousands of seconds, and eventually invades the full sample.
You have a gel in a box. You shine a laser, so you isolate a narrow cylinder.
Not exactly. So I have my plate rheometer. So this would be the plate. It turns like that. I am illuminating from the bottom, and I am picking up light backscattered. So I am integrating over the thickness of a sample.
All the sample.
All the sample. Okay. So it's like 0.5 millimeter or something like that, as opposed to the size of the plate. So from an experiment like that, I am not able, for example, to tell whether these active parts are midway in the gap, close to the bottom, close to the...
Rotate two rotating plates.
I'm doing a creep experiment, so I'm fixing the stress, and very slowly the sample creeps like that.
By twisting like
Yes.
that. So what you see is that something happens somewhere on the boundary. You don't know where in height, but you see some kind of, you start to slide somewhere, and that propagates.
Right.
It could
The
be
fact that everything starts from the boundary should not be a big surprise, because this is a plate-plate geometry, and the stress and the strain are larger at the rim of your plate as compared. This is different from cone plate
It
geometry.
could happen close to a plate.
I'm sorry?
It could happen near one of the plates. You don't know.
It could.
slip.
What we do know is that post-mortem, we open a variometer like that, and we observe that the gel sticks to both plates. So this is not slip from one plate or whatever. It is really some kind of fracture and failure that has occurred in the bond. And you have to play chemical tricks to make sure that your agarose gel really sticks to the plates. Otherwise, yes, slip would be the thing that you observe. Okay, so this photon correlation imaging is quite powerful. Let's see, do I really want to say? No, I don't want to say anything about that. Okay, let me just not show this and go directly to this thing here. I have shown you what happens in this shear geometry. You can think about the same concepts applied to our geometries. For example, to us, this tensile geometry, tensile test is quite interesting. It's what you can do on polymer films or plastic materials and so forth. And you can sort of apply the same concepts. So you end up with a general way of thinking how this change in strain throughout your samples turns out in a decay of a correlation function. And this is what I have sort of recapped here. This is your correlation function. It is proportional to this intermediate scattering function. So far, this is not rheology specific. It's sort of a super general. Now, to make progress, I'm making wild assumptions everywhere, but they're not so wild. One assumption that makes your life much easier is to say, okay, look here, this is really shitty because you have a difference in position over time of a given particle and another particle, not the same particle. So it's not the self-motion that you are measuring. You are measuring the motion of each particle with respect to all other particles. And this is a pain in the neck. It turns out, luckily, that in most situations, this thing here is very, very close to its single particle counterpart. So basically, in this double sum, you throw out all cross terms, and you just keep the terms j equal k. In that case, this difference in position is just the amount of displacement of each particle over time tau. That makes your life much easier. And now you can rewrite this thing here. In this way, you say, okay, this I can just write this sum over all particles as an integral of the same term but which is weighted by the probability of actually observing a given displacement delta r, and then I integrate over all possible values of the displacement. This is just because this sum here I'm summing over all particles, but there will be particles that move more, particles that move less, and so in determining the value of this sum here, it is important to know what is the probability that any given particle will move by a given distance. Now, this thing here, I think I'm missing here a v. So this integral is over a volume, and the key point is what that volume is. This volume is the volume associated to one single speckle as measured on my detector. This is a little bit subtle but important point. If I'm doing the regular experiment, the far field experiment, I told you each speckle, each pixel receives light coming from the whole illuminated volume. So in that case, V, it's easy what this V here, it's the whole scattering volume. It's the portion of a sample which is illuminated by your beam. If I am doing my photon correlation imaging experiment, the one where I am imaging things, this is a little bit more tricky because actually I am taking an image of a sample. So if you imagine, for example, that you are shining your beam on this slab, and then you have speckles, well, each speckle, which corresponds to a small cylinder, if you wish, in the sample that has the same thickness, the same length as the thickness of the sample, because you get light from the whole thickness of the sample, but a lateral size which will be the lateral size of the speckles. Because now each speckle corresponds to a specific position on your sample. But once I have figured out what this V here, then I can do this thing here. And quiz, this is the last quiz. What is this integral? It looks like a simple Fourier transform. So it is a simple Fourier transform. It is a simple Fourier transform of the probability distribution of the displacements. So why do I say, yeah, haha, it's a simple Fourier transform? Because you have that loads of textbooks that tell you what the Fourier transform is of any conceivable function almost, and you have very effective numerical ways to calculate Fourier transforms. So if you can reduce your problem to a Fourier transform problem, then you are really in a good shape. For example, if you take simple shear along x, then the displacement will be only in the x direction. And if you have particles homogeneously distributed in your sample, the probability distribution of displacements at a given tau will be flat between 0, particles close to a fixed plate, to a maximum value, which is simply gamma dot times tau. And the Fourier transform of a function like that is very well known. It's a sinc function. I mean, it's not very important what exactly it is, but it's something that you can find out in textbooks. Okay, I will definitely stop here. And the next time I will briefly discuss how we can apply these ideas to various kinds of rheological tests, like oscillatory shear, startup shear, creep, and stuff like that. I will show you that there are easy things and less easy things, but in terms of coupling, scattering, and rheology, but we can deal with that. And then hopefully I will have some time to go through that. Thanks a lot.